Look at the International Space Station as it crosses the night side of Earth. On the sunlit side, exposed metal can climb toward the temperature of an oven. Minutes later, the same structure is in darkness and radiating heat away into the black sky. Nothing about the metal changed. The orbit did not stop, only the light disappeared. Now widen the view. The sun's core reaches roughly 15 million degrees Celsius. Its light crosses about 150 million kilometers of space and reaches your skin with enough energy to burn it. Yet the cosmic microwave background gives deep space an effective temperature of about 2.7 Kelvin, roughly minus 270 degrees Celsius. So here is the question: how can sunlight cross a nearly freezing universe without heating the universe on the way? And if the vacuum is so cold, why would an astronaut not become an ice statue instantly? The answer is stranger than the movie version. In a vacuum, cold is not a substance waiting to touch you. Heat moves by rules, and two of the rules you use every day simply vanish when the air is gone. Stay with me, because by the end we will connect one exposed astronaut, the James Webb Space Telescope, the Moon, Mars, and the survival of Earth's atmosphere in one thermal story. We usually speak about cold as if it were a fluid. Cold air enters a room. Cold water pulls warmth out of your hand. But temperature is not a material that pours from one object into another. It is a measurement of how energy is distributed among particles and radiation. In a room, trillions of molecules collide with your skin every second. Their collective motion is what a thermometer reads. A warmer object has, on average, more microscopic energy available to exchange. A cooler object has less. The word cold is a shortcut for that difference. Deep space is almost empty. Between stars, there may be only a few particles in a cubic centimeter, and in the emptiest regions, even fewer. That is not a perfect mathematical vacuum, but it is so thin that the familiar crowd of collisions disappears. The vacuum itself is therefore not a freezer with a temperature pressing against your suit. A spacecraft can still have a temperature because its materials contain atoms, its electronics generate heat, and its surfaces absorb and emit radiation. But the empty space around it is not a block of cold matter. It is a route through which energy can escape. This distinction is the first key. A thing can be cold because its particles have little energy. A vacuum is different. There are hardly any particles there to carry a conventional temperature at all. Imagine the worst possible experiment, a person suddenly exposed to space without a helmet. Films usually show instant freezing, as if a giant freezer door opened. That is not the first danger. With no surrounding pressure, liquid water in exposed tissues begins to boil at body temperature. This is called ebullition. Saliva and moisture on the tongue can start forming vapor because the pressure has dropped, not because the water was heated by a flame. The lungs are even less forgiving. If a person holds their breath, expanding gas can injure the tissue. If they exhale quickly, the body still has only a short window before oxygen deprivation becomes fatal. The exact timeline depends on the situation, but unconsciousness arrives long before the body has time to freeze solid. The strange part is that the vacuum does not remove heat efficiently by contact. There is no cold air rushing across the skin, no liquid surrounding the body, and no dense gas carrying warmth away by convection. The body would lose heat mainly through infrared radiation, while exposed moisture boils and pressure damage begins. Space is lethal, but not for the simple reason the word minus 270 suggests. A temperature quoted for the cosmic background is not the temperature of an invisible wind touching your face. Heat has three everyday routes. The first is conduction, energy passed through touching matter. A metal spoon becomes hot because vibrating particles hand energy along its solid lattice. The second is convection. Warm fluid moves and carries energy with it. A breeze cools your skin because new air replaces air that has already picked up heat. Both routes need matter. Conduction needs particles touching. Convection needs a fluid that can circulate. A vacuum removes the outside air, so those two routes become dramatically weaker. The third route is radiation. Radiation does not need a material bridge. It is electromagnetic energy. Photons, leaving one object and traveling through space. Every warm object radiates. Your body radiates infrared light. A heated metal plate radiates. The sun radiates across the solar system. This is why the same spacecraft can be roasting on one side and freezing on the other. Its sun-facing surface absorbs sunlight. Its shaded surface has no warm air to refill its energy, so it radiates infrared photons toward the darkness. The final temperature is an energy balance, energy absorbed plus energy generated, compared with energy emitted. Think of a flashlight in a dark room. The beam travels through the air and reaches a wall. The wall absorbs the photons and warms. The air along the beam's path does not suddenly become as warm as the wall because most of the light passes through it. Sunlight behaves the same way in the vacuum. It is a stream of electromagnetic energy, not a hot wind. The photons cross empty space at the speed of light. They deposit energy when a surface absorbs them, a solar panel, a spacesuit, a planet, or your skin. The color of a surface matters. Dark coatings absorb more visible light. Reflective and metallic coatings reject part of the incoming solar energy. Infrared emissivity matters too. A good radiator can release heat efficiently while an insulating layer holds energy back. There is no contradiction in saying that a photon can travel through cold space and still burn you. The vacuum does not need to warm up first. The photon carries energy directly to the object that catches it. The station's orbit makes the principle visible. It circles Earth roughly every 90 minutes, moving between sunlight and shadow again and again. In sunlight, the exterior absorbs solar energy. In shadow, that input stops almost at once. The metal does not instantly become the cosmic background temperature. It has thermal mass. Its atoms are still vibrating, its batteries and electronics may still be generating heat, and different surfaces exchange energy internally. But without sunlight, its only route to the outside is radiation and whatever conductive paths the spacecraft engineers designed. The result is a brutal gradient. One panel may be intensely heated, while another panel, facing deep space, is losing energy. Thermal engineers use multi-layer insulation, radiators, heat pipes, coatings, and carefully chosen orientations to keep the structure inside a survivable range in orbit. Sunset is not simply darkness. It is the instant a spacecraft's energy budget changes. The James Webb Space Telescope turns this problem into its mission. Webb looks primarily at infrared light, the same broad family of radiation emitted by warm objects. If the telescope were warm, the telescope itself would glow in infrared and drown out the faint signals it was built to detect. So Webb does not merely tolerate the cold, it engineers a cold side. Its sunshield is roughly the size of a tennis court and is built from 5 separated layers of coated kapton. The layers do not touch. Each one blocks, reflects, and radiates part of the incoming energy before the next layer sees it. The vacuum between them is an excellent insulator against conduction. The hot side can reach around 85 degrees Celsius, while the protected observatory settles near 40 Kelvin, about -233 degrees Celsius. Webb's mid-infrared instrument needs an even colder environment and uses a mechanical cryocooler to approach only a few Kelvin above absolute zero. Notice the design lesson. Webb is not wrapped in a thick blanket that traps heat forever. It is open to space so unwanted infrared energy can radiate away. The shield controls what the telescope can see, and the radiators give heat a one-way path out. At the second Sun-Earth Lagrange point, about 1.5 million kilometers from Earth, the Sun, Earth, and Moon remain on the same side of the spacecraft. That geometry lets the shield do its job continuously. Webb survives the temperature paradox by turning it into a direction. If a vacuum has no ordinary air temperature, where does the famous -270 degrees come from? The number describes the cosmic microwave background, a bath of ancient photons left over from the early universe. About 380,000 years after the Big Bang, the universe became transparent enough for light to travel freely. That light has been traveling ever since, but space itself has expanded. As the universe expanded, the wavelengths of those photons stretched. Longer wavelengths correspond to lower photon energies. Today, the background radiation has an effective temperature close to 2.7 Kelvin, just above absolute zero. A thermometer designed to measure radiation can therefore report an effective temperature for the sky. It is not measuring a wind of cold atoms, it is measuring the energy distribution of the oldest light in the universe. That distinction also explains why a warm object in deep space can cool. Its surface emits infrared radiation into a sky whose background is only a few Kelvin. The object loses more energy than it receives until its own emission balances the incoming radiation and any internal heat. The universe is not an empty freezer, it is an almost empty room with an extraordinarily cold view. The moon is our nearest demonstration. It receives sunlight at nearly the same distance from the sun as Earth. Yet its surface swings from about 127 degrees Celsius in full sunlight to roughly minus 173 degrees Celsius in darkness. In permanently shadowed polar craters, measurements can fall below minus 246 degrees Celsius. Why does the moon experience such violence? It has no thick atmosphere to circulate heat around the surface. Its tenuous exosphere cannot redistribute energy the way Earth's air and oceans do. Sunlit rock absorbs photons. When the sun sets, the rock radiates directly toward the black sky. The moon's polar shadows add another twist. Some crater floors never see direct sunlight because the crater walls block the low sun. They become cold traps, preserving water ice and other volatiles for geological timescales. The moon is not farther from the sun than we are. It simply lacks the thermal blanket that spreads energy and releases it slowly. Mars shows the same principle on a planetary scale. Evidence from ancient river valleys, lake beds, and minerals tells us that early Mars was not always the frozen desert we see today. It once had a thicker atmosphere and stable surface water in places. Over time, Mars lost much of its atmosphere. The planet is smaller than Earth and lacks Earth's global magnetic protection. Solar wind and atmospheric escape processes helped remove gases over billions of years. As the air thinned, the planet became worse at holding and redistributing heat. Today, Mars can be sunlit and still bitterly cold overall. The problem is not that the sun stopped shining. The problem is that a thin atmosphere cannot store enough energy through the night or move it efficiently around the planet. Mars did not simply freeze because it was a little farther away. It lost the material system that made sunlight useful after sunset. Earth's atmosphere is astonishingly thin compared with the planet beneath it, about 100 kilometers from the surface to the conventional edge of space. On a globe, it is closer to a skin than a shell, yet that skin changes everything. Air, water vapor, clouds, oceans and land exchange energy. The atmosphere absorbs and re-emits infrared radiation. Greenhouse gases do not create heat from nothing. They slow the escape of heat, giving the surface a more stable energy budget. The oceans store enormous amounts of energy. Winds and currents move it. Clouds reflect some sunlight and also absorb outgoing infrared. The atmosphere is not a perfect blanket, and Earth still has deserts, polar nights, and dangerous extremes, but it prevents the day-night switch from becoming a lunar-scale catastrophe. The light touching your face is the same kind of energy that reaches the moon. The difference is the system around you: air, water, rock, and a planet large enough to hold them. We can now answer the opening question in one sentence. Sunlight crosses cold space because light carries energy without needing to heat the vacuum, and objects in space gain or lose heat mainly by absorbing and emitting radiation. The astronaut does not freeze instantly because there is no cold atmosphere touching the body. The immediate danger is pressure loss, boiling moisture, and oxygen starvation. The spacecraft does not have one universal temperature because each surface sees a different balance of sunlight, shade, internal heat, and infrared radiation. Webb survives by making the balance directional. The moon swings wildly because it has almost no blanket. Mars is a warning about losing one. Earth remains habitable because a thin atmosphere and deep oceans turn violent radiation swings into a climate system, and the number -270 degrees, that is not the temperature of nothing. It is the faint thermal signature of the oldest light still filling the universe. The next time sunlight warms your face, remember what is really happening. Photons crossed an immense, nearly empty distance without warming the root. They warmed you only when your skin caught them. Around you, an invisible layer of air slowed the escape of that energy. Beneath you, an ocean and a planet carried the rest. You are not protected from space by a thick wall. You are separated from it by a delicate atmospheric skin, a planetary version of the smallest useful blanket. If this changed the way you think about cold, subscribe to the Stellar Cosmos for more calm, evidence-led journeys through the strangest places in the universe. Tell us in the comments, what space paradox should we unpack next? Until then, keep looking up, and remember that even empty space has a story written in light.